Rotating cutter shafts turn at different speeds, 45 RPM on one shaft and 30 RPM on the other. Clean waste was prepared in identical sets for tests in 3 different shredders. Steel pipe and other waste was wrapped in plastic to simulate nuclear waste packaging. This is a 600 horsepower hydraulic drive low-speed shredder. Beneath the visible waste are steel pipes, angle iron, channel iron, a Freon tank, record holders, a tape recorder, electrical conduit, and chain link fencing. The particle size of the shredded waste from the machine was larger than desired, but was acceptable. Keep your eye on the tire. Now watch the shed. The rock is the remains of a drum of 800 psi mortar from a previous test. The mortar is soft and does not shred easily, but note that it did not hamper shredding. In fact, the rock often helps move waste into the cutter. This is the same kind of waste you just saw being shredded, except that it was shredded in the 80 horsepower electric drive shredder. This box of shredded waste was segregated into its original parts. Most of the waste is reduced to a good size for further processing, but some of the waste comes out in long strips or relatively long steel bars and pipes. Our process in the transuranic waste treatment facility calls for incineration of the waste immediately after shredding. We can tolerate the longer pieces, but prefer shorter ones. In our next series of tests, we will attempt to reduce the overall length of the shredded waste item. We concluded that the waste cannot be effectively separated or classified after shredding, and that decontamination of shredded waste is not feasible because of material deformation and entrapment of contaminants. This unshreddable item was placed in the midst of other waste inside a drum. Whereas we will x-ray all drums before they are shredded in the transuranic waste treatment facility, it would obviously be desirable to process drums even though they are known to contain some unshreddable item. If the shredder can shred the drum and contents, leaving the unshreddable item on top for removal by manipulators, then the test would be an unqualified success. In the center of the picture, down between the cutters, you can see the unshreddable item. Again, you can see that the mortar does not hamper the ongoing shredding. As you've noted by now, the shredder shafts automatically reverse when they encounter an unshreddable item. In this way, the shredder does not destroy itself. As you can see, the objectives of this test have been met. Unshreddable items do not cause problems. This is a sample of waste which was melted into basalt, a hard black rock which can only be sectioned with diamond saws. Unlike the soft mortar, this hard rock is handled easily by the shredder. If the hopper were filled full of mortar or basalt, the weight would force the rocks down into the cutter teeth and greatly improve the shredding efficiency. This is 1/8" stainless steel. We actually shredded 1/2" stainless steel plate on this machine, but it takes time and is not recommended. The drum in the foreground is the 800 psi mortar in its early stage of shredding. This is 3/4" steel cable. This old typewriter and other similar equipment process easily. An electrical company provided this electrical cable and several of the following test items. In our shredder test, we attempted to shred everything we thought might cause a problem. The 800 psi mortar was the least shreddable item, but it does shred at about 1,400 pounds per hour per drum. In addition to what you will see shredded in this presentation, we shredded case-hardened chain, 1-inch rebar, 1/4" plate steel, computer paper, heavy plastic, 2-inch plexiglass, clothes, computer tapes, inner tubes, hard hats, bandsaw blades, fire hose connectors, 3-inch gate valves, 6-inch channel iron, and a railroad track connecting iron. The shredder was actually designed to process aluminum bales like this one. For other types of waste, the shredding efficiency can be altered by rearranging, resizing, and reshaping the cutter wheels, and by changing the rotational speed of the shaft. The use of low-speed shredders to shred whole drums and boxes filled with nuclear waste offers enormous cost and time savings over the alternative of dismantling each waste container remotely with manipulators. Testing on whole boxes was limited to a single test because only one of the shredders had a hopper large enough to accommodate a box. As you will see, the test proves that a box can be shredded. This is the third shredder tested, a 400 horsepower hydraulic drive unit and a 4x4x4 foot wooden box. In condensing our lengthy tests in 3 cities to this 8-minute presentation, we have by necessity shown the best footage. There were delays when the cutters could not grab a box or drum. In our test, an average drum required only 2 1/2 minutes to shred, even with the delay. We can beat that throughput rate considerably by shredding several drums simultaneously. The shredding of this box only lasts 1 minute on film, but it actually required 15 minutes. We hope to improve this rate with further testing and modifications. Even if we don't succeed, 8,000 pounds per hour is more than adequate. At the conclusion of the shredder tests, we purchased this 160 horsepower electric drive 4-shaft low-speed shredder for further in-depth testing. Several tests and modifications are planned to develop optimum capability to shred large waste containers.
Okay, tell me what we're looking at, Joe.
This is a piece of heavy gauge sheet metal which has rags entrapped in the crimps caused by the shredder.
Okay. Is this, what is this material? Where did it come from? What is it?
This is municipal refuse which has passed through a primary shredder, and this is the magnetic fraction which was extracted by the magnet. But the shredding process crimped up a lot of the steel and entrapped non-ferrous material.
Okay, so our intent is to put it through a VIP separator, see if we can disassociate the trash or from the metal. Okay.
This is the Williams VIP separator.
Okay, you want to point to the parts?
It consists of a vibrating pan conveyor, which is going to be loaded with feed on the feed end here. It'll be caused to move down the conveyor and drop off at this point. After dropping off of the feeder, it's engaged by an air blast generated by this fan. The air velocity is going to carry the paper, rags, and other light fraction across the air knife and drop it into the shredding chamber in this hammer mill. The heavy material, which can't be supported by the air blast, falls into this duct and comes out this pipe into the heavy discharge area. The material that entered the shredder is given a shredding action which will disassociate the entangled rags, paper, and light fraction from the steel, and will be caused to go through the grate bars or be caught up in the airstream and report to the dust collector. The shreddable material is going to pass through the grate bars at the bottom of the shredder. What is unshreddable and hasn't made its exit through the heavy's discharge is redirected by the curved hopper back to the feeder, which will then be conveyed for another opportunity to drop to the heavy metals fraction.
Thank you. second run, and this is the material that has come off from the lights section, okay? Pour that out, please. Okay. Was there, okay, Joe? Want to describe anything you see? Just light fraction, right?
This is light fraction, essentially free of any metals.
All right. Thank you. Please show the discharge that came down the heavy spout. Okay. You have any heavy metal in there?
That's
You're lifting a little bit too. Don't lift it as high. That's it. Keep it right.
That's a 1/4-inch plate. Here's a piece of a casting.
Basically, that's heavy material.
Yes, it's mostly heavier than the tin can stock.
All right. Take out the metal that came through the grates.
Yes, sir.
Just drop it through there. Go ahead, John. Give him some help.
Yeah.
Okay, Joe, if you look through that.
This fraction is containing mostly tin can scrap, and it had gone into the shredder and through the shredder grate bars, and by so doing it liberated the paper and the rags which were tangled in the metal previously.
Okay, thank you. Now, can we take a look at the rags and all?
Okay. Yeah, let's move this over
here. Okay, just dump it out. All right. Okay, thank you. Joe, would you walk behind? No, I'll just back up now so we can see the tree pile. Okay. Okay, I guess that's it. Start sorting through that material then?
Yes, sir.
And what have you got there?
Here's some wire.
Okay, well,
Here's some larger pieces of ferrous.
you want to get in there too. All right. Large ferrous?
Yes,
Right.
sir.
What else?
Here's some pins, clean pins.
Okay. What do you want to show them?
Show the fabrics,
Okay,
The top.
just point to whatever you want to talk about.
Show the fabrics and the
Fabrics.
plastic.
Fabrics or where? Okay.
All right, let him do that. Robert, he knows what he wants, huh?
Yeah.
plastics,
Okay.
some bent tubing.
All right, we'll load this up into a drum and feed it into the system as the first test.
Okay, it enters the vibratory pan feeder at this point, shakes down where it passes over an air knife. Air is generated by this fan down here, blows up through this duct past the material. The heavy material drops off and exits through this chute and is collected down here in the pan. The rest of the feed enters the ring rotor crusher where it is pulverized and oversized is directed back up through the chamber and back into the feeder for another pass over the air knife. The fine material, the crushed material, exits the crusher and is collected down below. The fine vertible paper and cloth, it exits at the top and is collected in the cyclone.
Okay, we'll see the cyclone in a minute. Okay, what do you got?
There we go. 20 and, how much? 12 pounds. 108.
108, 108 pounds. Okay, would you dump it out for me, please? Yeah, it's just like that. Come on. Mess around with it a little bit, Dave, with your hand, shovel or whatever. Fall through the middle. All right, thank you. Now, can we get the heavies? Would you please get the heavies?
Okay, 13 pounds.
13 pounds. Could you please put them out? Just Okay, Dave, would you? That's fine, right there. Yeah, show me the big piece if you will. Don't lift it up. Okay, thank you. How about the fine material now? Where at?
£4.
4 pounds, all right. Okay, Dave, would you show me that paper, please? All right. Okay, thank you. In the picture.
Okay, this is the other view on the opposite side of the system.
Not towards the camera, Dave.
You have the feed that drops down onto the vibratory feeder
Right.
here. It drops into the shredder, which is right over in this area. This is the upper chamber. This duct that you see here is return air that travels down here to the air knife.
Okay, that's the recycle air of the air knife. Okay.
This is the motor that drives the ring rotor. This is the line that goes to the motor that powers the ring rotor hammer mill. This line.
Show me what you get.
Okay, the feed. This is the view of the system on the opposite side. Now the feed drops down into the vibratory conveyor, which is located here. It enters and crosses the air knife. This is the hammer mill section down in here, driven by the motor. The chamber is in this area. This duct is the return line, recirculating air line to the air knife fan.
Okay, and show me the exhaust.
Okay, the exhaust line is right here. It takes the material, the light material, paper, plastics, etc., to the bag house.
Okay, and I'm going to zoom back, Dave, now. And would you please then point out to me the exhaust lines that we have here, where they...
Okay. This line
All right.
is the return air, recirculating air for the air knife.
Okay.
It's drawn from up above in the top of the chamber.
Okay. So
Draws
that's
down,
our recirculation line.
right.
Right.
It goes down into the air knife fan.
Okay.
And this duct channels the air right up here to this area,
Okay.
and this is where the air knife
And
action
show me
takes
where
place.
the air is taken off, please. To the
Okay.
exhaust bag house.
The air is taken off from up here,
All right.
travels through this duct, and then is collected in the cyclone collector.
Okay, well, show me the fan first. Goes to that fan,
Goes through this fan,
then goes up that ductwork.
goes up the duct and into the cyclone collector.
All right.
And we
And it comes
retrieve
over
the
here to
product
this
from-
cyclone.
from
And the
barrel.
product from the cyclone then discharges to
Into
this
the barrel.
barrel. All right. Got this new batch around. This is the second.
Yes, it's the second drum.
There's a wire, a little wire in there.